Good morning, everybody. Welcome to our day 2 of our Future of Technology series, Giving Hydrogen the Green Light. My name is Philippa Oldham and I'm Stakeholder Engagement Director at the Advanced Propulsion Centre. Welcome back to those of you that joined us yesterday and thanks for joining us today for those of you who are new to these sessions. So today our focus is looking at the supply development and future direction, looking at to integrate and share some of that know-how and knowledge transfer whilst looking at finding challenging solutions and to understanding the problems and balancing the energy system, but also taking a look around the impacts of life cycle analysis and what this means as we potentially transition over towards hydrogen. And I'm delighted actually that we're covering that today because there were a number of questions yesterday around life cycle analysis. So I'm delighted that we will be able to hopefully answer some of those that were posed then. So today I'm joined by 4 fantastic speakers. We've got a keynote being provided by Colette Cohen, who is the Chief Executive of the OGTC. We're joined by 3 panelists, Brian Mabin, who's Head of Advanced Technologies at Wrigtbus, Joe Howes, who's Principal Consultant at E4tech, and Gareth Williams, who's Strategic Director for the National Composites Centre.
So I'm actually going to set a little bit of context, I hope, really, because I feel that hydrogen has become a bit of a buzzword and for many and one of the sort of solutions going forward, but without really any context. So I'm going to bring you back a little bit into the fact that we're currently in the 4th industrial revolution. And that is important for a number of reasons. Ultimately, you know, we've moved from sort of steam and mechanism through to mass production through electricity, and then the computing, and think of the impact and how much things changed in the late 19th or 20th century with the advent of computers. And then towards the very end, we started moving into this, what they call the intelligence industrial revolution, more around our mobile phones, artificial intelligence, the connected world. But I think it's even bigger than that. And that's what I want to kind of push into your minds, in that this is the first time we're really in an industrial revolution that goes beyond the factory, goes outside of the workplace. This is the first time where we're really meshing home and work and the very essence of how we live. And I think that's actually been emphasized by our current conditions in the pandemic. We're working from home, and the way we've used data and the way we communicate and the way the world is really connected. And it's not just about data, it's about biological. Think of how many of you, use your phones or your watches. They're like little mini computers now, connecting your health as well as your working ability. So a very different world that we're living in. And yet that backdrop is in also one of the biggest, most amazing changes we've seen around climate change and the acceptance that how we're changing and how we're interacting with the planet is having a massive impact on the planet. And so, we quite often simplify things in these conversations to being, it's about fossil fuels. And that's why the conversation today around hydrogen and the future of transportation, to my mind, is super relevant. Because I challenge that it's definitely about fossil fuels, but it's also about how we live. It's about how in just 2 generations, we have across the globe incredibly different carbon footprints. Europe has embraced the EV. So many people, as part of this audience is probably quite big champions of the electric vehicle. And I would say that it's one of the winners of the current industrial revolution and the impact of climate change. But I would challenge that it may not be the final solution. And that as a result, there's some real questions around what are the other options that we could be looking at. And so the answer is quite complex. And as Philippa mentioned, it's what's the supply going to look like? How are we really going to evolve and move on this journey? And so I want to take a moment to bring you to the North Sea and look at what does transition look like. Whoops. And I find this one of the most enabling sort of descriptions of the energy transition. I get that it's only for the UK. There's a much bigger picture out there. But if you look at it from the perspective of the UK, this captures how a whole basin, but an energy system, will change from 2020 through to 2050. And I'm using in this case just the CCC data. It changes. I mean, there's even been updates on these numbers since I put them in because of the new CCC report, but it gives you the essence of it. And there's a couple of key messages that I want to try and sort of bring to you. The first is the pictures on the right-hand side. What you see in 2019 is kind of what the North Sea looks like today. Predominantly oil and gas, some wind farms. But the expectation by 2050 is that we're going to have a really integrated energy basin. And there's a number of reasons. And actually, harking back to the EVs, one of the drivers of this need for a big change in the North Sea, because electrical generation is going to become critical to our overall transition to a net zero future. So I'll bring you to the bubbles. You can see that currently the value generation and the delivery of energy right now in 2020 is predominantly oil and gas. The pie is about 24 billion in value, and it's mostly delivered through oil and gas. But that changes with time. Oil and gas diminishes, not only in demand, but in its ability to deliver from the North Sea. We see a huge growth in delivery in wind. And I would challenge that the volumes that we've even encountered here in this particular profile from the CCC are not aspirational enough and will not deliver the level of electricity we need for a truly electrified nation that we seem to be driving towards. It looks at hydrogen production. You can see virtually zero now to quite a large amount of hydrogen going forward. And there's a big CCUS delivery. And that actually is tied to the assumptions currently in the CCC report are that you're going to have quite a bit of blue hydrogen. And blue hydrogen requires carbon sequestration to meet its blue credentials. But the thing that you should take away from this, because I think a lot of people think that oil and gas are kind of in competition with the new energy generation opportunities. And we're not really, because the pie becomes bigger. The pie actually gets nearly twice the size of or it is over twice the size of the current pie. So if you look 2020, 24 billion in value. By 2050, this energy profile is worth nearly 50 billion pounds a year. So there is enough opportunity and enough room for everybody. And I think, you know, there's elements here that means that it's an opportunity for all of us to work together. But if as a nation we're going to deliver net zero, we kind of have to work together. But it also says that EVs are not the only option. And actually, we're going to have to start looking at all sorts of energy generation. And that's not just for cars, because ultimately we're going to need power generation in many forms. And why hydrogen becomes super important in this scenario is really because of its flexibility. And that's sort of what we want to start looking at. We have limited amounts of hydrogen today, like 27 terawatt hours. We're expecting to need at least 270 terawatt hours by 2050. I would suggest it's even more than that because of the flexibility that hydrogen gives you. One of our biggest challenges when we look at the increased demand of electricity in the grid is that where we will generate this electricity, which will be particularly in our growth scenarios, which is around floating wind, North Sea, best wind, best reliability, is not actually where you need electricity. So we're going to have to find really good, economic, efficient ways of moving that electricity to where you need it. And ultimately that means being able to change that electricity into some other form of power. So that's when hydrogen starts becoming super important. But for all, and I think this is the crux of the conversation we're having today, for all of our current new energy sources, we have a challenge. We've seen onshore wind and shallow wind reducing costs. really dramatically over the last 10 or 15 years. But with CCUS, blue hydrogen, green hydrogen, we have technologies that will enable them, but they're not affordable. They're all expensive. And ultimately, if we need a just transition, if we need to move to a new world, we need one that's actually affordable to everybody. And at the moment, that's not where we're at. So that's why these conversations with APC, and you're going to hear from Gareth and the catapults later, innovation is really important. Currently, as I've said, blue requires CCUS, which obviously makes it expensive. Green requires a huge amount of power. So we need to innovate to bring the opportunity that hydrogen could provide to us as a nation into an affordable place. And why is that important? Well, ultimately, hydrogen has a role in mobility, a much greater role than maybe people want to think about. It has a greater energy capacity. It's mobile, it's flexible. This concept of how do you get all of that power you've generated from the place where it's not needed, which is north of Shetland, down to south of the M4. How do you do that? Hydrogen is one of your sort of best solutions for that. But it also has a greater flexibility in that it also has a role in heavy industry. It can, this really allows us to start replacing oil and gas. One of the reasons that there is a transition is that oil and gas has for many years been a single solution to many demands and needs, from high heat generation for glass manufacturing and cement manufacturing through to turning on your gas hob in your house and delivering your dinner, getting into your car, getting into a plane, one source. Okay, we know within our industry that it's really multiple sources of a similar product, but ultimately hydrocarbon has answered a very clear demand. On top of that, it answers nearly 19,000 daily products that we use, from our shampoo to the ink in our pens, are all have a hydrocarbon base. So there's a lot of things that need to change. And to find an alternative product that has a high level of flexibility is really valuable to us when we start looking at this transition. And hydrogen is one of those products. The other thing that's really advantageous to the UK is that we are quite rich in potential. So this is the part where we talk about a transition. If you think about, we can't move directly to green generated hydrogen. The amount of wind required is more than 10 times the amount of wind we have today to allow us to supply the EV expectation, to supply the normal electricity, to then increase that because we're trying to electrify more homes, to then have spare capacity to make hydrogen. We are nowhere close to having that capability at the moment with with renewable generation. So there is a transition, and that's where blue hydrogen becomes really important, because it would allow us to begin this hydrogen economy, to start generating and developing hydrogen solutions, but also start thinking about how you connect the UK with a hydrogen backbone, which in fairness is already being considered by a number of the electricity supply companies. And then you can start moving hydrogen through the country, but that provides opportunity. It may be for power at the moment, but that becomes an opportunity for other distributed networks for hydrogen. And we do have blue hydrogen generation potential around the country. So while the green is predominantly going to be north of Scotland, actually blue has opportunities all across the country right now. And there are projects that are looking at that from this southern and central North Sea, all the way through up into the northeast of Scotland, East Irish Sea, Central Belt. I mean, there's really great activity already going on around both blue and green hydrogen. And so that's what makes it quite exciting and a major opportunity for the UK. So we have natural assets, we have skills, we have capability, we have projects, and this is a good start. But the other thing that we need to really think about, and I know Gareth will talk about this a little bit more, is that hydrogen is an end-to-end challenge. And what I mean by that is, it's not just about, well, if we manage to generate it, we're good. Or if we create the demand, we're good. Actually, we need to work out how to generate it, transport it, store it, use it, deliver it. And each element of that has its own technical challenges, which means that this is truly an end-to-end challenge, that this has sort of crosses multiple sectors, and it doesn't care whether you're a car sector or an oil and gas sector or, you know, a pipeline provider. Some of the problems are common. So there's problems that are around pipes, pressure vessels, conversion efficiency, storage. All of those can then become common challenges where in reality we could work together. So if you take that sort of an attitude and you look at this complexity of the challenge, this is where we really need to start thinking about, how are we going to innovate? How are we going to make all of this work so that we don't double dip, that we don't compete, that in actual fact we share our learnings and we really accelerate the delivery of hydrogen into the UK sector and actually become really good at this really fast so that we can export it to other nations. And that's important for a number of reasons. As we move particularly to the green generation in the future, we are perceived by Europe to be the largest generator of green hydrogen if you look at EU numbers. So we do have this big export potential, but we have to kind of get after it now if we're going to be the nation that becomes sort of the leading hydrogen economy. So this creates, for me, another opportunity. It creates an opportunity for collaboration. And I think this is part of the conversation today and what Philippa teed up at the beginning. Because it's not a generation problem or a supply problem or a demand problem, but actually an end-to-end challenge that crosses generation, transportation, storage. It's a problem that we can work on together. So I see this as one of the opportunities for us to come together cross-sector, the different technology organizations, the different industries, under some sort of a clear hydrogen strategy where we can develop, share results and really use both government funding and industrial funding to drive the change that we need. And I would say that many of us are already thinking about this. The catapults and OGTC, which I sort of represent, are already working on things like the Hydrogen Innovation Initiative. St. Andrews, in fairness, has already put in a hydrogen accelerator. We need a nationally connected hydrogen technology concept where we have these hydrogen accelerators, we have projects going on, but they're all connected and they're all in service of like a national mission to become a hydrogen economy. I believe that we actually have, as a nation, the skills to do it. We have the natural resources. We have the capacity, both intellectual and financial. But I would say so far that our approach is disconnected, goodwill-based, and quite sporadic. That if we're actually going to win this as a kind of global challenge, we need an industry-led commitment to hydrogen economy. And we need that to be supported by government. And government is important because not only does it seed initial funding and allow you to accelerate through those early innovation phases, but by setting the right policy and setting the right targets, volumes that we want to deliver as a nation, that we're going to use hydrogen power, you know, within industry or for planes or whatever we decide we want to do. Once that's identified, industry will then find a way to supply that. But you need that clarity. So even if you think about it, there was a commitment to, you know, getting rid of petrol and diesel cars and moving to EVs. That drove a whole, industry to prepare to have the EVs. You see a whole other sector now looking at how you power those and how you recharge. So once you set that expectation through policy, you create the environment and the ecosystem you need for industry and supply chain to come in and fill it. And I think we also need to create a focus on our own innovation and our ability to manufacture. So that means we need to develop our own capability, our own IP, and we need to ensure that we're developing the sort of the skills and the education system to support it. So we have the next generation of skilled workers. But we also need to have clarity of the roadmap, because if, technically skilled people in oil and gas are going to move to new generation energy, we need to see what that looks like. They need to be able to say, if I'm an electrical engineer here, I can see my future over there. So we need to put the work in to be able to, help people see their future in this new world. I would finish on, I think hydrogen offers an amazing opportunity to the UK, but there are many countries in this race. And I think that if we don't get into action with clear intent, and we don't get a commitment that the UK wants to become a hydrogen economy, then we're going to miss this opportunity. And this opportunity is hugely valuable. And it's a massive opportunity for our industrial sector, our supply chain, and next generation, but also in our commitment as a nation to net zero. Thank you.
Thanks, Claire. That's absolutely brilliant and really good on perfect timing as well. So thank you. I've got a question actually, which you're covering slightly at the last point about the skills and the transition of those skills. I mean, we're seeing obviously in the auto sector that transition from internal combustion to electrification. How hard is it, do you see, for the transition of those potentially working in oil and gas at the moment over to hydrogen? Are they the same skill set? And who is sort of working on helping retrain some of those engineers?
It's a brilliant question. It's one of my bugbears at the moment. I'm a Just Transition Commissioner for Scotland, and I'm also on the Energy Skills Alliance, which is designed to try and work out that transition. And it's really challenging because we talk about hydrogen, we talk about wind, but the pace of investment and the pace of delivery of those new energy supply sort of systems is really slow. And actually the delivery of a new wind farm can be 10 years. So if we don't start moving that faster, it's very hard to say to somebody who's in oil and gas today what that job will look like tomorrow, because tomorrow might be 5 or 7 years away. And that's a long time for an individual to sort of look forward and say, okay, I fit there. However, if we could really sort of show how these jobs are being created, what the roles are, what the factories look like, what we're going to be manufacturing, how we're going to be delivering, that would build credibility and build understanding. So I think it's that we need to have a little bit more granularity in our strategies and plans to sort of say, particularly what we're going to manufacture and what we're going to put into the North Sea. Then you can start saying there is a transfer of skills, but you can also say where you need to reskill. And I think reskilling is a really important element, because currently our average age in the North Sea is about 43. Well, that's another 22 years on average of work life for most of those people. That they are definitely skilled individuals that you should be transferring to the next generation of energy. So we need to work out how to do it.
And I suppose maybe a call for action of anybody listening to this who's got children doing GCSEs or A-levels, is a great opportunity here for them to develop the skill sets there.
And if they are listening, think data. Data analytics, gaming, all that sort of stuff. Parents worry about that, but actually we're doing so much in that space about, visualizing, twinning facilities that they're really good skills to build.
Fantastic. Right, I'm hoping we're going to go live to Colin Matthews, who's going to ask a question. Colin, are you there?
Opie, yeah, can you hear me?
I can hear you, Colin.
Good, right. I've put 3 questions in there, but I'll ask the first one. Given that yesterday Baroness Brown told the Select Committee that the green hydrogen priority is to replace grey hydrogen in the first instance in industry, and to do so, it needs 200 terawatt hours of consistent electricity generation? Where and when will this be built to meet this demand? And where does the associated 20 billion litres of demineralized water come from?
So I'll apologise, Colin, in that I didn't see Baroness Brown's comments, so I can't talk specifically to the numbers, but I can certainly make a couple of comments around that and maybe it would help. One, I'll say the demineralized water is an assumption on the solution, and I wouldn't actually at this point say that we know definitively what the green generation solution is. I think that's one of the areas where innovation is still required, and there's some really interesting electrolyzer technologies that are being developed at the moment, some even without membranes, which would be like really transformative. So I think there's some work that needs to be done there. I think the volume that she's talked about is probably quite correct. That's what I said. I think currently we're underestimating hugely the amount of hydrogen that we'd actually need to use in industrial space and to replace hydrocarbon that we use today. So that's one of the problems and opportunities we have, in that if we really want to accelerate to green, we have to truly accelerate, particularly our wind generation capability in the North Sea. So, and alternative technology solutions. And even then, if you think about it, even if you committed today that you were going to quadruple your, well, actually, we've already committed to quadruple our wind capacity by 2030. And that we believe can be done, but it's a real challenge. But there's no expectation that you could double that again. And just getting the quadruple increase is only going to meet, to a great extent, expected domestic demand, not getting into the huge industrial demand side that we're now talking about for hydrogen. So I think it's good for them to be having these conversations. It's good to put out numbers and expectation, but that would require a complete paradigm shift in our approach to the acceleration of hydrogen generation within the country.
Can I come back with that?
Yeah, go on, Colin.
Yeah. Well, the other thing is, you talk about wind, but wind is intermittent. We need consistent electricity because of the consistent demand across industry. So we need to look beyond just the wind and solar. We need perhaps more nuclear to be able to give the base load that industrial demand will need. Yeah,
that's true, and it's kind of not true at the same time nowadays. I agree, but that's why we're thinking of what they would call a North Sea grid, so that if you actually have wind generation with excess capacity across the North Sea, you would do two things. You would have consistent power generation at all times for the base load, but you would also have excess during high wind, and this is where hydrogen and things like that become really important, where you convert that into alternative power sources, so that I mean, the North Sea, one of the reasons that platforms didn't convert to, I don't know if you remember, but years ago, people used to talk about, well, we could just put a wind turbine on the side of a platform. And the reason that people didn't do it is because it's so inconsistent. However, if you have so many wind farms across the North Sea in different areas, you pretty much have wind somewhere all the time. And that's the concept. And then if you have excess capability, you're turning that into an alternative power source. So during that period where you maybe don't have full capacity for baseload, you have alternatives like hydrogen or fuel cells generated so that they provide that, you kick directly into that. So I think they're definitely looking at that consistency as a priority.
Yeah, but you're absolutely right. I mean, the wind blows 27% of the time in the UK. So to have 200 terawatt hours, you effectively need 800 terawatts of wind turbines to accommodate for that, to hope that it's going to be blowing in the right place at the right time.
It doesn't quite work like that, but I think we probably won't talk about anything that could take a very long time, because it is about excess capacity in building. So that's where storage and that becomes so important.
As the name Wrigtbus implies, we are a manufacturer, designer and manufacturer of city buses. So we were formed 75 years ago in 1946. We're based in Ballymena in Northern Ireland. We are the manufacturer of the iconic new bus for London. We launched our first battery EV vehicle in 1999 and our first fuel cell EV vehicle in 2008. In 2019, we came under new ownership and were owned by Joe Bamford of the Bamford JCB family. We have an updated factory facility with significant capacity for growth. And we're very focused on zero emission buses, but we're focused both on battery EV and fuel cell EV. We believe that each of these technologies has pluses and minuses, and they're suitable for different environments. Two iconic projects we did in the past was the 1,000 new Routemaster hybrid electric vehicles in London and the streetcar hybrid electric 18-meter bus rapid transit vehicles for Las Vegas. I'm just going to share a few details about our zero emission product roadmap. This is our Generation 1 fuel cell EV double deck. Amongst other cities, there's 15 of these running in Aberdeen. This came on sale in 2020. Around 50 buses are already delivered and running on the road, and around 100 further bus orders are in place at the minute, and more will materialize. As I mentioned, we're also focused on battery electric. This is our Generation 2 battery electric vehicle. It's a double deck. This new vehicle is being launched in June 2021. It's available with the largest battery capacity in the UK industry for a double deck, which gives it the longest EV range. And 80 of these buses have been ordered by TransLink, the local operator in Northern Ireland. This is our Generation 2 fuel cell EV single deck, which is being designed at the minute. A driveline test mule for this new fuel cell EV technology demonstrator is being developed under the APC, Advanced Road to Market Demonstration Programme. And this test bus will be displayed at the CENEX Low Carbon Vehicle Exhibition in September 2021. We also have involvement in Advanced Propulsion Centre 17 programme. And under this programme, which will start for us in May 2021, we plan to develop a complete new family of fuel cell EV buses, utilising new driveline technology and an integrated supply chain. And these are designed for export around world markets. So we're going to have a new fuel cell EV 12-meter single deck bus, a new fuel cell EV 18-meter articulated bus, a new 10.6-meter 2-axle double deck, and a new 12-meter 3-axle double deck. And there's very much a pull in the international market for these types of vehicles. There's more demand than there is supply, and this gives Wrigtbus lots of opportunities for growth and for export. So what is a fuel cell EV? A fuel cell, to start off with, is a solid state device that converts hydrogen from onboard storage tanks and oxygen from the background air into electrical energy. That electrical energy is then used to charge a small battery. And from that point onwards, it really operates the same as a battery electric vehicle. We have an electric traction system, and the battery allows the recuperation of energy during braking. The only emission at the point of use is distilled water. Some waste heat is created, which is very useful because in the winter we can use that to heat the passenger saloon. The hydrogen refueling process, so a complete fill of hydrogen, takes between 7 and 8 minutes. And hydrogen, as Colette mentioned before, can be produced from surplus renewable electricity. And this is classified as green hydrogen, and it also helps to balance the electricity grid. Some advantages of fuel cell EV over battery EV, especially in the bus market. The bus daily range is typically much higher. a battery EV vehicle, even our vehicle with 432 kilowatt hours of batteries, can only achieve 190 miles. Now that's okay for inner city and somewhere like London, but routes that are intercity or rural routes, it's nowhere near enough. And the problem is more batteries means more weight and more cost. The fuel cell EV can easily achieve more than 300 miles. The fuel cell EV performs much better when the passenger heating is needed in the winter, and it's very suitable for places like Dubai, Hong Kong, places where hot climate and you need aircon. Refueling time is only 78 minutes for fuel cell EV, whereas 3, 4, even 6 hours is needed to charge a battery electric vehicle. Buses want to operate 22 or even 23 hours a day. Fuel cell EV is the only option if the bus garage is far away from a 33 kV electrical grid supply. 100 buses can need the same electricity supply as 5,000 houses, so it's pretty significant amount of electrical energy. For a 100 BEV bus garage, significant additional land is needed to allow the installation of all the individual EV battery chargers. And probably important for Wrigtbus is that there seems to be many more international opportunities for us to sell fuel cell EV buses compared to battery EV buses, which is dominated by Chinese bus suppliers. So the map on the left shows some hydrogen production sites. Some of these are brown hydrogen, blue hydrogen, and some of them will be green hydrogen. The long-term plan is that we want to harness surplus wind power to produce green hydrogen. However, much more investment is needed in the UK green hydrogen production and distribution system. And this can only be really achieved through government coordination. So how do we, until the natural gas pipeline conveys hydrogen, how do we actually get the hydrogen into the buses? It's actually reasonably straightforward. The image on the left shows a 2-trailer system. So you have, you're using one trailer, and these are hydrogen tube trailers to fill the bus, whereas the other one is being replaced. They broadcast their remaining capacity using telematics, which means the truck turns up before it's needed. The image on the right shows what you need for 100 buses per day. So if you have a rural bus operation, this is easily achievable rather than having to connect to a 33 kV electrical cable. Just for the engineers involved in the audience, a few details about components. This is our single deck vehicle. At the front of the vehicle, we do need a lithium battery to deal with the peaks and troughs and energy demand, and it needs cooling. We have hydrogen storage tanks, which store around 38 kilograms. We have a version for 50 kilograms as well. So that allows easily more than 300-mile daily range. We have the option of a 70 kilowatt fuel cell at the minute, or a 100 kilowatt fuel cell. That's the black item at the back. And of course, we still need an electric traction system in the same way as a battery electric bus. So we need a permanent magnet drive motor, we need a drive inverter system, and we need a high voltage power distribution system. So that was the slides that I wanted to cover.
So hello everybody, I'm from E4tech and I'm here to talk about how do we make sure that that hydrogen that's supplied to all of the uses that Colette talked about and to Brian's buses is low carbon, and what are the ways that we can do that, and how do we make sure that it happens? So as a quick introduction, E4tech is a sustainable energy consultancy based in London and in Lausanne in Switzerland. And we've been working on hydrogen and fuel cells, as well as other energy systems questions and low carbon transport generally for over 20 years. We also publish annually the Fuel Cell Industry Review, which is the leading annual review of what's going on in fuel cell markets and numbers of shipments and things like that. So you can download that if you're interested in some more data behind hydrogen and fuel cell deployments in the transport sector. Now, one of the areas that we look at a lot is the sustainability of these different options. And so that's what I'm going to be talking about today. So as Brian's just been discussing, we're talking about hydrogen in this forum today because there are lots of advantages of hydrogen fuel cell vehicles amongst all of the other options that we've got for decarbonising transport, which vary quite a lot depending on what mode you're talking about, the size and weight of a vehicle. And I just put in a graph here from the Hydrogen Council that showed where they see hydrogen fitting within the suite of low carbon options that you could have for different technologies. So lots of advantages to using hydrogen. But the question is, how do we make sure that we're getting the best options that we can from an environmental perspective? So the way that we look at this typically is through life cycle analysis, shortened to LCA. And this is a way of looking at all of the impacts of providing a service, in this case, transportation, driving a car a certain distance. And life cycle analysis takes into account all the parts of the life cycle of doing that. So what does it take to produce the vehicle? What does it take to produce the fuel? What are the impacts in using that fuel? And what are the impacts in the end of life of the vehicle? Now, you can do this across lots of different impacts. You could do it across water use or air pollution or all kinds of different things. But today I'm mostly going to be talking about greenhouse gas impacts because this is the key challenge really when we're talking about different hydrogen production routes. So we and others have done life cycle analysis studies that look across different types of vehicles. This is some analysis that we did in 2018, looking at different types of cars and looking at the greenhouse gas emissions, which are expressed in grams of CO2 per kilometre up here, and looking at how much of those come from producing and disposing of the vehicle, how much of those come from fuel production, how much come from actually using the fuel, carbon dioxide that comes out when you burn fossil fuels, for example, and how much comes from vehicle maintenance. I'm not going to talk through all of this, as I only have 10 minutes. The important point that I want to make is that for most of these different types of vehicle, most of the emissions are related to the fuel itself. You can see that from looking at the mid-blue fuel production and fuel use parts of these bars. And if you look at the area highlighted in green, which is the fuel cell electric vehicles, you can see that the numbers vary hugely. And the reason that these numbers vary hugely is due to this mid-blue fuel production bar, where the way in which you make the hydrogen has a huge impact on the greenhouse gas emissions. Colette talked a bit at the beginning about the different ways that you can make hydrogen. And there are many different ways to make hydrogen. If we draw a spider diagram of all the ways that we've thought about it, looks very, very complicated. So just as an overview, there are 4 ways that I've put on this slide, which include some of the ways that Colette was talking about. So you can use fossil fuels. So for example, natural gas, splitting that to produce hydrogen, and electrolysis using renewable electricity. They're typically the 2 main ways that people talk about. But importantly, there's also byproduct hydrogen from existing industrial processes. And there's also the option to produce hydrogen from biomass or even waste. So as I was saying, lots of different ways to produce hydrogen. This is a graph made by LBST, another consultancy who did this study for the Hydrogen Council that just shows the range of emissions factors that you can get depending on how you produce hydrogen. And this is only how you produce it. And as I said, a UK specific study on this that we've done together with LBST will be coming out later this year that we've done for BASE. But the important thing is that these purple boxes on the left-hand side, these different ways of producing hydrogen, you can't make generalizations about those and say, well, you know, this one's better than that one, because there are lots of different, very specific details of what the supply chain looks like for hydrogen, where it is, when it is, that really affect these greenhouse gas emissions. So a few things to bring out is use of grid electricity. Now, obviously, this is most important if you are running an electrolyzer off grid electricity, but it's actually also important for lots of other parts of the chains, compression, and any electricity use in any of these other chains, that if you are using grid electricity, then the difference you can see here between 2030 and 2050 is huge as grids decarbonize. And obviously the grid electricity factors between countries vary hugely as well. As Colette talked about, if you're going to enable blue hydrogen routes, if you're going to enable use of fossil fuels, then you need CCS. And you can see the big difference between these routes at the top, which are fossil without CCS, and those that include CCS that are down here. The ones at the bottom are typically renewables and nuclear routes that give very low greenhouse gas hydrogen results. And also biomass feedstocks give pretty low results, but that can vary quite a lot depending on the source of the biomass that you're using. Also, something that we've modeled in our study for Bayes, but is not modeled here, is routes that end up with negative emissions. And that could happen if you have a biomass route where effectively you're gasifying the biomass and taking the CO2 and sequestering it and then using the hydrogen. And if you store that CO2 permanently, then effectively you've got a negative emissions route. You've got something that's providing hydrogen as an energy carrier and also providing a carbon sink. But, you know, as mentioned before, this is an end-to-end system. Production of the hydrogen is not the end, it's the beginning. And there are lots and lots of different ways that hydrogen could be used in different sectors. And to get it from the point of production to the point of use, there could be a whole range of different downstream options to do with how you transport it, whether you compress it, to what extent you compress it, whether you liquefy it, how pure does it need to be, whether you convert it into a different kind of energy carrier like ammonia. And all of those have emissions. And emissions from some of these could actually be larger than the production emissions itself, depending on which production pathway that you've used. So there are big variations in these factors to do with, you know, as I said, whether you liquefy, how much electricity you use in this process, how far you transport, but there are also quite a lot of uncertainties. So, you know, if you put hydrogen through a pipeline, what contaminants does it have? And therefore, what do you need to do to purify it to use it in a vehicle? So I don't want to scare you all by these slides of saying there's a huge variation here, because these things are measurable and in lots of cases are manageable. But it's just important to do that to ensure that we get the savings that we want. And as you'll have seen, I mean, even the graphs that I've shown don't give you the same results for the same pathway. You can only do this by having a common methodology. And typically those common methodologies are codified in standards, and those standards are used to underpin various activities to make sure that we get the savings that we need. So there are voluntary standards that have been developed. So one of them most high profile ones at the moment is Certify, which is a voluntary scheme which is a guarantee of origin for green or low carbon hydrogen in Europe. In the UK, we also have policy that does this. So we have the Renewable Transport Fuel Obligation, which incentivizes use of renewable fuels, and hydrogen can count towards that. So renewable hydrogen can receive credits under that scheme as long as it meets sustainability criteria, including 60% greenhouse gas savings, though there's actually a consultation out on increasing that to 65 at the moment. And as we see more hydrogen use across the economy, there may be other policies developed that help to support hydrogen use across other sectors. And then you've got to work out how we develop a low carbon hydrogen system that works for everybody.
Hi everyone, pleasure to be speaking to you today. So we've had some great talks and presentations today on hydrogen and setting some of the scene for why hydrogen is picking up momentum. And what I want to reinforce here is to echo a few words that Colette said around the need for connected innovation and how important innovation is. So I'll set up some context of the Hydrogen Innovation Initiative, which is something that we're working on with a number of partners involved here. And then I'll go into a little bit more detail on a specific area of interest, obviously as the National Composites Centre, on some of the pressurised storage tanks that are very relevant for transportation. So current collaborators on this concept, very much looking at coming together and as a catapult network and the technology centres, so the OGTC, the APC, the ATI and NPL, with the catapult network, as I said, we came together and said, right, hydrogen is increasingly significant across all of our sectors. How do we accelerate the activity and make sure that we get the most value for the UK? So what we don't want to see is a hydrogen economy developed without the right investment in innovation and UK supply chains, so that we don't don't use this opportunity to actually develop the value in the UK supply chains. And we think that's really important. So between this network, it's kind of our roles in industry and innovation is to accelerate technology, the adoption of innovation, and to help drive that development in the UK for UK value. So hopefully none of these names are new to you. And what we've come together and we've developed this concept as a special purpose vehicle for the Hydrogen Innovation Initiative. And I'll go in a bit more detail as I go through. So the context and the rationale, so you'd see up in the top left, hopefully you recognize that from what Colette presented. It's a great diagram, schematic developed by Arup, which just highlights the concept, or a decent schematic of what the hydrogen economy looks like from end to end. And we found this really useful. So we went through and we overlaid some of the opportunities and the right to participate and the USPs of the UK in terms of abundant access to green energy, CO2 storage, locations, etc. And then we overlaid some of the technology challenges that really need to be addressed to make sure that we can generate hydrogen at a cost that works, distribute it from where it is generated to where it is consumed at a cost base that works to accelerate that technology in those consumption markets. And we recognize that that needs to be an end-to-end process, particularly if we need to accelerate it. In the middle, that also has to be supported by policy and the right standard and certification requirements for industry to actually adopt those technologies at an accelerated rate. So in particular, NPL's role in this is to help to identify the regulatory frameworks and the collectively the influence on policy that needs to be in place to help adopt those technologies so they don't become a barrier to entry. And as we came together a group, we were working on this for a number of months. The EU strategy was published, and there were some words in there that really chimed with why we had come together, and that was that we cannot, if we continue to innovate and develop technology in traditional sector-driven silos, we won't hit net neutrality in a cost-efficient way by 2050. So we need to build new links between sectors, between organizations, between places within nations, and between nations as well, because the hydrogen economy will go across borders, as many of our transportation methods will as well. So there's a number of organizations closely linked to government activity around supporting industry acceleration of these technologies. We want to play a more forthright role in helping industry move this forwards. But there are challenges, and we require coordinated intervention about both technical and non-technical issues to allow this to be accelerated efficiently. So we came together and we identified the need for a program of work. We called it end-to-end hydrogen, because it's really focused on the end-to-end activities and joining up those, the excellent work that everyone will do in their own sectors to make sure that we have a coordinated set of activities so that we have that efficient deployment. So we proposed to forge strategic linkages across the value chain and create a connected innovation backbone, really united against 4 things. First is driving a thriving hydrogen economy, so a key component to driving the UK to net zero. The second is to secure the UK as a hydrogen super supplier, so the domestic opportunity and also the export market opportunity that brings. To accelerate key technology innovations to secure the UK as a global leader in hydrogen related technology. And the fourth is, as we do all this, to make sure that we develop the UK value and the sovereign UK capabilities as we create these new supply chains. So we don't just solve the challenge by importing technology and then we're at on the reliance of overseas innovation development programs and incentives. So we had a very high level look across. So looking at, we broke the segments down to generation, distribution and consumption in terms of those markets, and then looked at the different technology challenges. And this is not exhaustive, this is just illustrative, because what we identified, as well as the technology challenges and the policy and non-technical gaps that need to be addressed within each sector, the technology innovation landscape, there's a lot of crossover between multiple sectors. And that's really important as you're going to develop new supply chains, for example, in pipeline technology. Every sector is going to require hydrogen transported in some form in a pipeline. So as you're creating it, you're seeding an industry with baseline IP, whether that's composite pipelines or non-metallic pipelines or other technologies that allow those pipelines to work with hydrogen, is to looking beyond those traditional markets and looking at adjacent markets to increase the business case for companies to enter those markets. And we're seeing that much more prevalent post-pandemic as companies are looking at beyond their traditional markets for future economic sustainability. So what do we propose to do? And this is still evolving and developing, but what we're trying to do is create a connected innovation ecosystem, specifically focusing on accelerating hydrogen technology. So there's great activity that will happen at academic level, but we want to make sure that for the key strategic priorities for the UK, that we have very good articulation of challenge-led research that are solving challenges that industry need. And through this mechanism, we also provide excellent routes for technology exploitation. At the kind of mid-TRL, which is very much where the catapults have been designed to help to bridge. We want to see that we have a strategic focus on the technologies that we're developing to help industry, and that we have a direct route to support industry to deploy those technologies to create that IP and then industrialize it with our partners and the funded programs, for example, the OGTC, APC, ATI is really their business as usual. In terms of doing that. So we looked across generation, distribution, consumption markets. There's multiple markets within that, but really essentially also what we're trying to really create is the cross-sectorial green threads, as I call them. So connecting how do you actually take green hydrogen, for example, where do you produce it? How do you distribute it? Where does it need to be for an aerospace market, for example? What's the infrastructure requirement for an airport? How does that connect with places? How does it connect with international hubs for air transport so that we have those roadmaps for deployment? And if we don't get that really clearly articulated for the strategic priorities, then you can imagine the amount of chaos that could ensue if we don't get this right. And innovation is going to be critical to accelerate things like cost down in all of these technologies, but increasing safety, decreasing weight in the system, for example. So as I said previously, we're creating a concept for a special purpose vehicle, so a single identifiable identity for us all to work within, that industry can engage with, that look at the funded enablers, the activities, the enabling technologies that the likes of the Catapult network need to develop and influence, and the access to facilities that industry need for testing, certification requirements, etc. And then how do we deploy those into industrial programs of work with industry and the collective partners within each sector. So I'm going to dive down a little bit more specifically on some of the technology challenges, and for the National Composites Centre, obviously the opportunity for composites. I'm going to still skim across this at a fairly high level. So across the value chains, we're looking at the generation requirements, offshore, onshore distribution, spoke distribution, so where you have actually local production rather than decentralized production versus centralized production, into the consumption markets, and then into energy generation as a consumption market as well. And the three priority products for composites that are going to add value across multiple sectors are pipes, pressure vessels, and cryogenic storage tanks. So there are various applications with known specifications, requirements for those technologies, and some that we're developing and working on with industry partners to identify what are the strategic priorities for those technologies, what are the challenges that industry needs support in solving, so that we can really truly accelerate these technologies. So some of this won't be a surprise to you, and E4tech obviously much well versed onto the economic side of this, but the value proposition of fuel cell electric vehicles and hydrogen propulsion is increasing, and you can see some great road mapping activity from the APC here that have identified the role that CFRP and composite tanks will play in that to actually reduce the weight requirements of that fuel cell fuel storage capacity for hydrogen. And a great study that I picked up with Deloitte in China really looked at the break-even points for fuel cell electric vehicles compared to some of the incumbent technologies. And they will vary in different markets, but the composite pressure vessels, because of the inherent cost of carbon and they're not prevalent in the market at the moment, there's a huge opportunity to actually drive down the cost, increase the innovation in those technologies for a mass market, production market that we'll need to get to really see us drive those costs down. So the role that we play at the NCC is very much around the design, materials, manufacture, and the certification of the latest technologies and composite technologies for these pressurized vehicles, looking at the next generation of smart tanks, automated technology for manufacture to really drive that cost base down, increase the reliability, and drive weight down even further in these tanks, which will enable much more efficient hydrogen propulsion systems and reduce the whole life of the cost of those vehicles for industry and increase adoption.
Our first question is going to come from Rebecca Watson. Are you there, Rebecca?
Every time I listen to these webinars, I always feel like it just feels like a no-brainer. There's clearly lots of amazing technology. There's clearly lots of opportunity, but obviously with opportunity comes competition. And I'm just wondering if the panelists have a view on what more government and or industry could be doing to ensure that we can maximise on these opportunities for the UK.
Colette, maybe, do you want to start off with an answer on that one?
Yeah, happy to. I mean, I completely agree. I think there's a lot of discussion and there is clearly a lot of opportunity, but it's hard to get in action because the reality is a lot of this is expensive and you can't just solve the problem locally because it won't be impactful enough. So it has to be across the UK. So we do need a little clarity on policy. So the hydrogen strategy that from the UK government is critical. And then turning that into meaningful policy becomes even more important. And I think the work that's also ongoing now on the innovation strategy is important because what we've talked about is there are technologies, but we've also highlighted some really big common challenges to making hydrogen in particular affordable as a net zero solution for the UK and globally. So there really needs to be as I've called it, kind of a national mission on how to drive the cost. We need to drive 30 to 50% of the costs out of the hydrogen agenda right now. So I think we do need some government intervention at this point. I know they're looking at it, but I think we need greater clarity and speed on that. I will say industry is moving anyway. I showed you some of those projects that are ongoing, but I think as Gareth has highlighted as well, connecting that all together into a sort of more homogenous solution is critical if this is going to work.
Yeah, if I answer also from the vehicle manufacturer's point of view, we have massive interest in our fuel cell EV vehicles, but the biggest impediment at the minute is availability of hydrogen and cost of hydrogen. The current cost of hydrogen is around £7 per kilogram, and it needs to get down to around £4 per kilogram to make hydrogen viable against diesel. However, of course, diesel will be prohibited. So therefore, do we really need to get down to £4 per kilogram? But yeah, it's only the UK government can give the coordination to get the right volume and distribution of hydrogen. I note, I can't remember the exact numbers, but France and Germany are putting in somewhere between 11 billion and 15 billion euros into hydrogen generation and distribution. And we don't have that same commitment at the minute in the UK.
I'll give a little bit of encouragement there. There has actually just been, under the North Sea transition sector deal, there's a £10 billion commitment between the industry and the UK government between now and 2030 on hydrogen production. So that's not everything, but that's a really encouraging thing. And that only just came out. Now we have to work out, how do you spend 10 billion wisely, quickly?
If I can add something to that, I think that, you know, excellent points from everyone. I think from a technology perspective and an infrastructure perspective, that connectivity you really need on the strategic priorities at least really needs to be in place. And those strategic priorities, you know, for the UK we need to be quite bold, as Brian's referenced, and we're hearing the start of that, like Colette's just referenced as well, that we need that certainty around the commitment to hydrogen, the investment opportunity available for it, because the challenge with hydrogen, we're going to go run at it really fast. Well, we need to run at it really fast, but there's a whole infrastructure piece around it. It's not as simple as just as electrification, which was presenting, you know, a huge amount of challenges for the infrastructure. But the good thing about hydrogen is it balances out some of those challenges that the electrification has, and I think we had some questions following Colette's around the challenge with capacity and demand, and hydrogen is a natural balancer for that. So I think having some bold commitments and some really strategic investment in priorities for the UK, not just in the industrialization, but also in the technology perspective, because, you know, there may be some markets in the short to medium term where you know, companies like Wrightbus or other technology providers might look at export markets to drive some of their costs down initially, in advance of serving the domestic market. So it's a pretty complex landscape to go and address, but clarity can help us really cut through some of that complexity.
Great. I've got a question in the box that I'm just going to ask directly. It's from Alan Thompson. And so it says, a prominent and rightly respected environmental campaigner has written that plastics must be eliminated because they are hydrocarbons, which have been echoed by others. This is confusing so many issues, and it seems to be an anti-petrochemical industry theme. It ignores not least the use of plastics for composite hydrogen tanks and wind turbine blades. However, is the oil and gas sector able to continue supplying polymer feedstock without the hydrocarbon combustion fuel product demand on the extraction economics? In other words, in a hydrogen economy, can the oil and gas sector achieve balance?
It's a really good challenge, and I don't think we know is the answer. You are seeing people like Saudi Aramco doubling down on delivery to their petrochemical refineries because they believe that's sort of their growth future. But I think if we're going to do that to avoid the creation of a different problem, we need to really be focusing on hydrocarbon plastics recycling. So if we think about, you know, the challenge of how we use plastics now, they are essential. And actually the pandemic has only reinforced that, because all of the hygiene elements are strongly hydrocarbon based. Everything we're using now for protection, PPE, all hydrocarbon based. So again, you're not going to be able to switch that off safely, and it's certainly not fair in emerging nations. But we do need to start thinking about a full cycle approach to those, how you make them, how you recover them, how you recycle them. Whether that can be put into an economics that's competitive with hydrocarbon combustion fuel products, really, I don't think that's completely known. But in fairness, that's the part that is a transition. There is quite a long period. And I think the other part to think about is whether you can consider the petrochemical plants in a different way, as being multi-product generators, so that you can kind of diversify those as well, so it changes the cost basis. I think there's work ahead of us, and that's, but going via blue hydrogen as well is one of the opportunities for this transition for the industry.
Thanks, Claire. Joe, I saw you came off mute. Have you got something to add?
Yeah, and I've sorted my video too. I was just going to add on that. We're doing a lot of work at the moment on other ways to replace plastics, so on bio-derived plastics, and also the potential for using carbon dioxide released from other processes to make plastics as well. So I think that recycling, use of bio, use of recycled carbon are all things that should be looked at.
Yeah, and I'd reinforce that we've got, as a national composites centre, we've invested heavily in an initiative called Sustainable Composites, which is addressing the future sustainability of composite materials, because we recognise, the most of those materials, so composites are required to help us transition, but they're also, dependent on the petroleum-derived feedstocks, and then you have an end-of-life issue. So, we're investing ahead of, I guess, market demand to try and solve those issues. A key initiative we've got called SUSWIND is addressing what was referenced before around the challenges of wind turbine blades. With OGTC are involved with that as well. And what you can start to do, I guess, longer term view is more sustainable feedstock opportunities, naturally derived resin systems, but there's also value in the deconstruction of those epoxy resins into base constituents as new feedstocks to feed other chemical processes. So
frozen.
Sorry, I had one
more.
more.
To switch off petroleum that can cut and
we've lost you, Gareth, for the moment. Sorry, Brian, did you want to come in?
Yeah, we have a choice in terms of storage tank, hydrogen storage tank. We have a choice of type 4 aluminium tanks, which are carbon fiber wound, or type 3 polymer tanks, which are also carbon fiber wound. The benefit of the polymer tanks is that they save weight, and as a result, the vehicle is more efficient and can carry more payload.
Gareth, did you want to come back with what you were ending with when we lost you?
Yeah, sorry, I don't know where I cut out. Yeah, it's just, when you start looking about, sustainability and circular economy, start looking at waste streams as feedstock materials. So the plastics that we have, how can we deconstruct them into this baseline constituents that can then feed the process? And we've got the same situation with CO2, where the whole CCUS challenge needs to be solved. At the moment, the main bulk solution is to pump it back underground, but there's a value proposition there around using CO2 and potentially combining with hydrogen as well to create new materials and lock that CO2 into an embodied material that can get used for products or chemical constituents. So I think there's a huge opportunity in that space to solve that. Whether the economics stack up for, can petroleum producers still, if you switched off petroleum use for consumption and fuels, does it still economically work as a feedstock? I can't answer that question, but I think that's the key term of transition, isn't it? It's not a line in the sand where we go from one state to the next. It's how do we start transitioning an economy into a more sustainable future.
Thanks, Gareth, and thanks for that last point. Actually, very important across this this whole agenda as we transition towards net zero. So that's all we've got time, in the essence of time, for today. I'd like to thank my speakers very much for attending. It's been really insightful today. I've learned a lot, definitely.